from scratch. This is episode 4, the CAP Theorem. This is probably the most famous result in all of distributed systems. It's also the most misunderstood. You've seen the bumper sticker version. It's in every blog post, every system design interview, every tech talk introduction. Consistency, availability, partition tolerance. Pick two. It's clean, it's memorable, and it's misleading. By the end of this episode, you'll understand what CAP actually says, what it doesn't say, and why a better framework exists. The story starts in the year 2000. Eric Brewer, a computer scientist at Berkeley, presented a conjecture at the PODC conference. He proposed that it's impossible for a distributed system to simultaneously provide all three of consistency, availability, and partition tolerance. 2 years later, in 2002, Seth Gilbert and Nancy Lynch at MIT formally proved this conjecture. It became a theorem, but somewhere between the proof and the blog posts, the nuance got lost. Let's define the three properties precisely. This matters because casual definitions cause most of the confusion. C is for consistency, but this isn't the C from ACID that's about database invariance. CAPS C means linearizability, the strongest consistency model. Linearizability means every read returns the most recent write, or an error. All nodes see the same data at the same time. If you write x equals 5 to node A, then immediately read x from node B, you must get 5, not some stale value, not it'll get there eventually. 5 or an error. This is a very strong guarantee. A is for availability. This means every request to a non-failing node receives a non-error response. Notice what this doesn't say. It doesn't say the response is correct or up to date. It just says you get a response. No timeouts, no service unavailable, no hanging connections. If a node is up, it responds. The response might be stale. Node B might return x equals 3 when the latest value is 5, but it has to return something. P is for partition tolerance. This means the system continues to function when the network between nodes is broken. A network partition is when messages between two groups of nodes are lost or delayed indefinitely. Think, a fiber cable gets cut between two data centers, or a switch fails and half your cluster can't talk to the other half. Here's the critical point. In any real distributed system deployed across multiple machines, partitions will happen. They are not hypothetical. Google, Amazon, Microsoft, they all experience partitions. It's a fact of operating at scale. So here's the classic CAP triangle: C at the top, A and P at the bottom corners. The theorem says you can have at most two. The edges represent the pairs. CP systems on the left, consistent and partition tolerant. AP systems on the right, available and partition tolerant. And CA at the bottom, consistent and available, but only when there are no partitions. But there's a problem with this framing. Pick 2 is wrong because it implies you have a free choice among three equal options. You don't. You don't get to pick whether partitions happen. Partitions are a fact of nature in distributed systems. Networks fail. It's not a feature you can opt out of. So P is not optional. You always need partition tolerance, which means the real choice is when a partition occurs, and it will occur, do you sacrifice consistency or availability? That's the actual CAP theorem, not three choices. One binary decision made under duress. So the real question is, during a partition, do you want your system to be correct or available? Correct means reject request rather than serve stale or conflicting data. Available means always respond even if the data might be out of date. This is a binary decision that you, the system designer, must make. And it's a hard one because both options have real costs. Let me make this concrete. You have two nodes, node A and node B. Node A has the latest value of x. It's 5. Node B has a stale value, x equals 3. Now a network partition happens. Node A and node B can't communicate. A client comes in and reads X from node B. What do you do? The CP choice. Node B knows it might be behind, so it returns an error. Sorry, I can't serve this right now. Consistent, but the client is unhappy. The AP choice. Node B returns X equals 3. It's stale, but the client got a response. Available, but the data might be wrong. Neither answer is great. That's the trade-off. That's CAP. Let's look at CP systems, those that choose consistency during partitions. MongoDB with majority read concern. If the primary is partitioned away from the majority of replicas, writes are rejected. The system becomes partially unavailable, but guarantees correctness. etcd and Zookeeper. These are consensus-based coordination services. They use Raft or Zaby to maintain strong consistency. If a quorum can't be reached because of a partition, the minority side simply stops serving requests. Better to be down than wrong. You choose CP when correctness is non-negotiable. Bank account balances, inventory counts, leader election, distributed logs. Now, AP systems, those that choose availability during partitions. Cassandra, every node can serve reads and writes. During a partition, both sides keep operating independently. When the partition heals, conflicts are resolved using last write wins timestamps. REAC, another Dynamo-style database, used vector clocks instead, which we covered in episode 3. Same problem, two different conflict resolution strategies. Amazon's DynamoDB, designed from the ground up for always-on operation. The original Dynamo paper at Amazon was motivated by the shopping cart. The philosophy was a customer should always be able to add items to their cart, even during infrastructure failures. You can reconcile conflicts later, but losing a sale is unacceptable. You choose AP when uptime matters more than instant correctness. Social media feeds, DNS, caching layers, shopping carts. What about CA? Consistent and available, but not partition tolerant. This only makes sense if you can guarantee the network never partitions. In practice, that means a single node database. PostgreSQL running on one machine. It's consistent, it's available, and since there's only one node, there's no network to partition. But the moment you add a second node, a replica, a shard, anything, network partitions become possible. And you are back to choosing between CP and AP. So CA systems exist, but they are not really distributed systems. They are single machines. Here's something important. 12 years after proposing the theorem, Eric Brewer himself published a clarification. He wrote, the 2 of 3 formulation was always misleading because it tended to oversimplify the tensions among properties. The creator of CAP thinks the bumper sticker is misleading. Let's understand why with 3 key nuances. Nuance 1, partitions are rare. CAP only forces a choice during a partition. And in a well-run data center, the network is healthy more than 99.9% of the time. When the network is fine, you can have both consistency and availability. There's no trade-off during normal operation. So the question isn't, is your system CP or AP? It's, what's your default behavior during the rare moments when the network splits? Nuance 2. Consistency is a spectrum, not a binary. CAP's C means linearizability, the absolute strongest consistency model. But between linearizability and total chaos, there's a whole spectrum. Eventual consistency, writes propagate eventually, but you might read stale data. That's what Cassandra and DNS offer. Causal consistency respects the happens before relation we learned in episode 3. Weaker than linearizability but much cheaper. Sequential consistency. All nodes see operations in the same order, though not necessarily in real-time order. And linearizability at the top, real-time ordering. Spanner and CockroachDB achieve this, but at a cost. Many applications don't need linearizability. Causal consistency is often enough, and it's much easier to achieve with high availability. Nuance 3, the choice is per operation, not per system. You don't have to make a single global decision. The same system can make different choices for different data. Account balance, CP. A stale balance is dangerous. Better to return an error than show the wrong number. Profile photo, AP. If a user sees their old photo for a few seconds after updating, nobody cares. Better to show something than an error. This is how mature distributed systems actually work. They make fine-grained CP/AP decisions based on what the data means to the business. All of this leads to a better framework. In 2012, Daniel Abadi proposed PACELC, spelled PACELC. The insight is simple. CAP only talks about what happens during a partition, but partitions are rare. What about the other 99.9% of the time? PACELC works like this. It's an if-else statement. If there's a partition, choose between availability and consistency. This is the CAP part, same as before. Else, when the network is healthy, choose between latency and consistency. That second half is the new insight. Even when everything is working perfectly, there's still a trade-off. Stronger consistency requires more coordination between nodes, which takes more time. Weaker consistency can be served faster from a single node without waiting for agreement. Let's classify some real systems. Google Spanner, PC/EC. During a partition, it chooses consistency, rejects requests. During normal operation, it also chooses consistency. It uses TrueTime and Paxos for linearizable reads, accepting higher latency as the cost. Cassandra, PA/EL. During a partition, it stays available. During normal operation, it favors latency. Reads from a single replica, eventually consistent. MongoDB, PC/EL. During a partition, it chooses consistency with majority reads, but during normal operation, it can read from secondaries for speed, trading consistency for latency. DynamoDB, PA/EL. Always available, always fast, eventually consistent. CockroachDB, PC/EC. Like Spanner, it always chooses consistency, both during and after partitions. This gives you a much richer picture than the simple CAP triangle. So where does this leave us? CAP is a starting point for understanding trade-offs, not a design methodology. The real engineering is more nuanced. First, decide per operation, not per system. Different data has different consistency needs. Second, know where you are on the consistency spectrum. You probably don't need linearizability everywhere. Third, design for partition recovery, not just partition survival. How does your system converge after the partition heals? This is often harder than the partition itself. And fourth, use PACELC to reason about the normal case. Most of the time, the network is fine and your trade-off is latency versus consistency. Let's recap. 1. Partitions are not optional. The real CAP choice is consistency or availability during a partition. 2. CP systems sacrifice availability for correctness. etctd, Spanner, Zookeeper use when correctness is critical. 3. AP systems sacrifice consistency for uptime. Cassandra, DynamoDB use when availability is critical. 4. Consistency is a spectrum from eventual to linearizable. Most applications don't need the strongest level. 5. PACELC extends CAP to the normal case. Even without partitions, you trade latency for consistency. In the next episode, we dive deep into that consistency spectrum. Linearizability, sequential consistency, causal consistency, eventual consistency. What does each one actually guarantee? What can go wrong with each? And when is the weakest model surprisingly sufficient? This is where theory meets database design. That's episode 4. The CAP theorem, what it actually says, what it doesn't, and why PACELC is the better way to think about distributed system trade-offs. Next time, consistency models. Thanks for watching.